This is FE Peer Review. The date is September the 23rd, 2021. A few of my favorite maps. I thought I'd follow up my last video with a few more images. I'm not going to go into depth on any of them. I just thought I'd fill in a few gaps. Some of the comments I got were really quite fun and suggested ideas on what I might want to look at or what we might all want to see in the way of maps. So we're going to explore that here. I wanted to go back to a little definition I had offered as not to be the last word on the subject, but just as a way of kind of focusing on what the issue is. Maps are tools which relate information to specific locations in space. I think that's a good, useful definition. There are probably others as well. And before we get into it all, I wanted to touch once more on the issue of the Droppity map, because that was one of the things that came up in some comments. So I thought I would just quickly review this. It is a measure of Earth curvature with reference to a single point. And that's the key here. In the previous video, I had offered this image of a map of France with a Droppity map made for a point in the city of Limoges. Now, when I prepared this for the last video, I did it quickly and wasn't particularly concerned about what Droppity information I was providing. It is nonetheless accurate in that each of these rings represents a line of equal Droppity with respect to a point in Limoges. How much Droppity I wasn't really concerned about when I drew the map. I just wanted to provide a conceptual example. But for this video, I thought I would do a more careful version of the same. So what we have here is, again, we have Limoges, and we have a series of concentric circles around the city of Limoges. And what we are seeing with the outermost circle, from a height of 100 meters above the surface of the ground in Limoges, the horizon line of a sphere with the radius of the Earth. So the distance you would see to the horizon line of a sphere with the radius of the Earth with no atmospheric refraction considered. We're just looking at this in purely geometric terms. So that's the outer circle there. The next circle is the same, but for a height of 50 meters. And then the next is 20, 10, 5, and you can't really see it, but 2. So we have a Droppity map here that gives us useful Droppity lines for various heights from a point in the city of Limoges. Now, as I had mentioned before, that's just great if you happen to live in Limoges, but the nature of a map is that it's something you generally use in a number of different places. So this map here doesn't tell you anything about Droppity anywhere else in the country. For that, we would need to elaborate this map and provide similar data for other parts of the country, which is what I've done here. I've provided the same data for the other major cities scattered around France. And that is all great. That's just fine and dandy. However, were you to produce such a map, it being only useful where the cities are, you might find that, from what I know of the people in this country where I live, which I love very much, you might find that the people in the suburbs are rather offended at having been left out. I mean, why should the people in the cities be given a Droppity map, but then people in the suburbs can't use it? It's useless to a large part of the population. So really, we need a Droppity map that not only covers the cities, but also covers the surrounding suburbs. And that would look something like this. So now we've got the people in the suburbs satisfied, but I live in a small town. It's like 10,000 people in this little conglomeration of villages where I live. And I can assure you that if the French government were to produce such a Droppity map, we'd all put on our yellow jackets and go out in the street and say, well, what about us? You know, just because we don't live in the city or the suburbs and we're not feeding into the big city economy and we're out here in the countryside, we shouldn't be neglected and ignored. We really ought to be included as well. So there's a Droppity map that covers most of the small towns and larger villages across France. And now almost nobody's been left out. I have left out the very smallest of hamlets. And you would find that in certain parts of the country, in particular the Massif Central, which is very lightly populated, there would still be some Droppity zones that would need to be mapped before everybody's satisfied. But anyway, that gives you an idea, generally, the problem with Droppity maps. which is probably why we don't see them. So that may answer the question that was presented by a certain unemployed actor who I mentioned in the previous video about why we don't show Droppity on maps, because it would look something like this, and basically it would render the map as a communication tool practically useless. This here is Mount Fuji, one of the most recognizable mountains in the world due to its perfectly conical shape. I bring it up because there seems to be a bit of confusion on the part of a few people who are concerned about why drop is or isn't shown on maps. A bit of confusion between drop and topography. And I wanted to discuss topography briefly, as well as to share the topographic map of Mount Fuji. I think it's an amazing little bit of mapping, that cone shape just radiating out of this center point here. It's just so beautifully clear. Mount Fuji is a bump on the landscape. That's topography. It effectively has nothing to do with Earth curvature and drop. It's a different issue. Of course, they're all a part of the same object, so they're related, but the bump on the landscape is a separate thing from the overall shape of the entire object. And that's what topography is all about, the bump. And drop is all about the overall shape. Topographic maps, they came about as a result of this 1774 Schehallien experiment, which Mr. Sensible covered in a video a few weeks back. I'm going to be covering it as well in a few weeks when I do a video on gravity anomalies. And the Schehallien experiment the purpose of it was to measure the mass of the Earth, to determine the density of the Earth. And to do that, they need a mountain. They needed a mountain. Well, they found a mountain up in Scotland called Schehallien, which served their purposes really well. But in order to use it, they had to develop a system to determine the volume of the mountain. And in the process of doing that, they invented the approach of topographic lines, which is what we see in this beautiful map of Mount Fuji. Before we leave the subject of topographic maps, let's take a look here at something a little different from Mount Fuji. This is Yosemite Valley in the eastern mountains of California, the Sierra Nevada mountains. Yosemite Valley is one of my favorite places in the world. I used to visit it a lot when I was a child. On the left, we see El Capitan, this great cliff here, and beyond Half Dome, and around behind this, and you can't see it in this photo, is the Yosemite Falls. Let's take a look at a topographic map of that. Glorious chaos compared to those perfect concentric rings of Mount Fuji. We've got El Capitan on the center left, where I'm circling my mouse. We've got nice even topo lines up above, and then all of a sudden this crashing pile up of lines, one on top of the other, until you get down to the valley floor. It's a long drop. And coming around behind El Capitan, in the middle here, it says Yosemite Falls. Let's take a look at that. Yosemite Falls is 768 meters high. I've forgotten how many feet that is. Well over 2,000 feet. If it were a single waterfall, it would have been far and away the longest drop of all the waterfalls in the world. But it's broken into three parts, the upper falls and middle cascade and the lower falls. So it's not considered the tallest waterfall in the world. But we can see it on the map here. We've got the upper plains above Yosemite Valley, and then we have the first upper falls where the lines are dark and close together. That's the cliff above. And then we have the cascade coming through here. And then finally, where I'm circling the mouse again, the lower falls. You can hike right up to here on a very nice, easy trail to the base of the lower falls. It's quite an amazing experience. One last thing before we leave the subject of topographic maps. Here's something fun that you can do with them. Now, these are topographic maps at a much smaller scale. The maps we were looking at, the individual topographic lines represented differences in ground elevation of perhaps many feet or meters, even as much as 5 meters or 10 meters. But you could just as well do a topographic map where each line represents a change in elevation of 0.5 meter or 2 feet or whatever convenient size you want. When I was a student in architecture school, our teachers would give us a topographic map of a building site, and that was to be the site for our design project for the semester. And we would make models. Now, these are beautiful professionally made models, but we'd use the same technique using cheaper materials. I often did it using corrugated cardboard. You just take the lines and trace them onto sheets of corrugated cardboard, cut them out with a good sharp utility knife, stack them up, and you've got a beautiful three-dimensional landscape to work with while you do your design. Let's talk about isolines, everybody's favorite subject, isolines. Isolines are lines on a map which identify a constant value on that map. So our Droppity lines, those were constant values, and so they were isolines, as were our topographic lines. They could also be considered isolines. However, these isolines that you see on these maps have nothing to do with the shape of the earth or the topography of the ground. These isolines are, well, these maps are from the residential building code that's commonly used across the United States, and they identify structural design criteria. We have seismic design categories, for example. This is the eastern half of the United States, and the lines define the zones of more or less seismicity. So if you're designing in this dark patch here, you've got to go by much more strict criteria as far as the design for earthquake. The map on the right-hand page is wind design, and specifically the shaded zones are areas where special design is required, which means that the building code does not provide all the information necessary. Local jurisdictions have more information, and engineering will very likely be required. There are also wind maps for the rest of the country, which relate to criteria where basically anybody, if you're a homeowner and you want to design your own house, so long as you follow a certain paragraph in the code and you're in a certain wind zone, you're okay. But if you happen to be in one of these dark shaded zones, it's going to be a lot harder, because this is, of course, where hurricanes happen. So those are isolines and some useful maps that I use on a daily basis in my work. This is Urtha in the lobby of the Delorme Corporation in Yarmouth, Maine. Delorme is a map maker. And Urtha, according to Wikipedia, is the largest rotating globe in the world. It's 41 feet in diameter, which is about 12.7 meters, and it's at a scale of 1 to 1 million of the Earth. On that globe there, San Francisco, which is a 7 mile by 7 mile square approximately, would be about just under a half an inch in each direction. And Mount Everest, from the surface from mean sea level to the top of Mount Everest, would be about 3/8 of an inch or 9 millimeters. So that kind of gives you a good sense of scale. That's that globe there. Mount Everest would be 9 millimeters high. San Francisco would be 3/8 of an inch, 9 millimeters across, and it wouldn't really be very practical as a way to get around. Hard to keep in your glove compartment of your car or in the cockpit of your airplane. So that's probably one reason why we don't actually use physical three-dimensional maps that are globes. When we print them out, we are reduced to printing them on a flat sheet of paper, replete with all the distortions. Fortunately, with digital technology now, we can bypass almost all of that. So Wikipedia said this is the largest rotating globe in the world, but when I first looked it up, I wasn't paying attention to the word rotating, and I know of a much bigger globe, and it's a whole lot of fun. If ever you happen to be in Oberhausen, Germany, this is the gasometer. It's a former gas tank that has been repurposed into a kind of museum and exhibition space. The ground level has changing exhibits. And then from the first level up to the top, it's one big, vast, open interior space, 100 meters high. And there in the middle of it is this magnificent object. It's actually, I believe it may actually be a balloon if I remember right. Anyway, it's a kind of a sphere, a plain white sphere that hangs from the roof of the gasometer, and then satellite imagery of Earth is projected onto it through a whole bunch of lights all around, projectors all around. It's the most amazing thing to experience. It's pitch black inside, darker than this photograph suggests. And you can just barely see the steps when you walk in there. You sit down on this sort of amphitheater seating, and you lean back and you look up, and you're lost in this blackness with that amazing vast sphere of Earth floating above you. After a few minutes, you literally feel weightless, like as if you're just floating in space with this amazing, beautiful object there. It's, let me get the numbers here, it's 25 meters in diameter. That's about 82 feet. And that makes it about twice the size of the one we just looked at, or to scale, it's roughly 1 to 510,000. So, and if you're ever in Oberhausen, western part of Germany, get to the gasometer. It's an unforgettable experience. I think I'll end this map thing with this little, beautiful little object. Fascinating little piece. I think quite a few of these have been found. This is from Mesopotamia, and I highly recommend this guy's video. I will put it in the comments. He's a professor, Babylonian, I don't know. Anyway, it's a very interesting video, and he's talking about what's significant about this little clay tablet here. Because what we see on it is a map, a real map, not just a symbolic representation of a piece of land that had been around for a long time. This was carefully drawn, dimensioned, and all of the and given areas. The areas are there, the dimensions are there, and it's all accurate. Now, it's not drawn to scale per se, but the lines and the areas that are calculated all match and all fit together just right. This is one of the earliest known maps, and it was describing a piece of land. There was a land sale happening, and a piece of land that was being bought by one person who also owned this other piece here. It had this complicated shape, and they measured it. It's amazing. It's quite a fun video. So there's one of the earliest maps for you. And I think I'll end with that. No place to end quite like the beginning. So I wish you all a very pleasant evening, and I hope you enjoyed this. This is FE Peer Review. Remember to click that like button on your way out the door. Have a great evening. Bye-bye.